That is lecture 2 of week 2 for course microprocessor programming and interfacing. Course code is CS430. Before we start discussing today's lecture topics, we have to review previous lecture. In previous lecture, we have covered all the data addressing modes that are direct addressing, displacement addressing, register indirect addressing, register relative addressing, base plus index addressing, base relative plus index addressing, scaled index addressing. And so in this lecture, we are going to discuss first of all program memory addressing modes. First program memory addressing mode is direct program memory addressing. That mode deals with the far type of instructions, and full 1 megabyte memory will be in reach during direct program memory addressing. Second type of program memory addressing is relative program memory addressing, and there are two types of jumps in this type of addressing: short jump and near jump. Both will be discussed by using some examples. Then third type of program memory addressing is the indirect program memory addressing. In indirect program memory addressing, you will be using some operand, or you may say that new IP will be loaded by using some indirect reference to register or memory. Then we have to discuss program memory addressing mode by using push and pop operations. So these addressing modes will be discussed. After that, we have to start a new topic of assembly to machine language conversion, and format for machine code will be discussed, and some tables will be required to convert assembly language to machine code. Those tables also discussed during this lecture. So first of all, we have to cover program memory addressing modes. As the name shows, that is related to the program memory, and program memory is code segment. So during this discussion, we will be considering code segment and instruction pointer register of microprocessor. So as we have discussed earlier, that there are three types of program memory addressing modes: direct program memory addressing, relative program memory addressing, indirect program memory addressing. And for studying these three addressing modes, we have to consider jump instruction. So now we are going to discuss these three modes. First one is direct program memory addressing. So general format for jump instruction of direct program memory addressing type will be that written here in this slide: jump address 1 colon address 2. So there will be two 16-bit addresses separated with colon sign written with JMP mnemonic of instruction. So operation is that address 1 will be moving into code segment register and address 2 will be moving into IP register. And machine language is also shown here that uh, jump instruction of direct program memory addressing type will be stored in 5 bytes. First byte will be of opcode. EA is the opcode for direct jump, and remaining 4 bytes are for IP and CS. After opcode, you have to store IP. Lower byte of IP will be stored, then higher byte of IP will be stored, then you will be having lower byte of CS, then you will be having higher byte of CS. So according to the instruction, IP is loaded with address 2, so IP low will be address to lower byte and IP high will be address to higher byte, and CS low will be address 1 lower byte and CS high means address 1 higher byte. So this jump is called intersegment jump or a fast jump. It will cover whole real memory, that is 1 megabyte. In 1 megabyte memory you may jump anywhere by using direct jump. One of the example is given here, JMP 1020 hex colon 3040 hex. So when this instruction will be executed by microprocessor, code segment register will be having address 1, that is 1020 hex, and instruction pointer register will be having address 2, that is 3040 hex. When you will be writing this jump instruction in your program, assembler will be converting it into machine code, and machine code for this instruction will be EA is the opcode for fast jump or direct jump. Then there will be lower byte of IP, that is 340, then IP higher byte 30, then lower byte for CS, that is 20, and then higher byte of CS, that is 10. So that jump instruction, jump 1020 hex colon 3040 hex, will be stored in 5 bytes. First byte for opcode, then 2 bytes for IP, then 2 bytes for CS. Second type of program memory addressing mode is relative program memory addressing. For relative program memory addressing, jump instruction general format is JMP label or 16-bit address. Operation of this type of jump is current value of IP will be added with displacement and you will be getting new value for IP. So that is mentioned here that IPN will be loaded with IPC plus displacement and you will be jumping to the new location, new IP. Displacement mentioned here is a signed number. If your displacement is within 8-bit signed number limit, that is displacement is greater than or equal to minus 80h, or displacement is less than or equal to 7fh, then that displacement may be stored in a byte. So your jump will be of short type. First byte for opcode, that is EB, and there will be a single byte for displacement. But if your displacement is exceeding that limit, that means displacement is lesser than minus 80h or displacement is greater than plus 7fh, then your jump will be of near type. or you may say that displacement may not be written in 1 byte. 2 bytes are required for storing displacement. So your jump will be stored as a near jump. Opcode for near jump is E9, and then you will be storing lower byte for displacement. Then you will be storing higher byte for displacement. So your near jump instruction will be of 3 bytes, while short jump will be of 2 bytes. Now we are going to explain how a short jump will be stored in memory, or if that is not a short jump, that will be a near jump, and how near jump will be stored in memory. So we have taken an example. We have taken a program. First instruction is move ax comma bx, that is written at offset 100 within code segment. So that instruction is of 2 bytes. So next instruction of jump 010 jump 010a will be stored at 102 offset within code segment. So we consider this instruction as short jump. So that will be of 2 bytes. Next instruction will be at offset 104, and that instruction is add dx comma cx. And at offset address 10a within code segment, we are having an instruction of push ax. So that is the our value for our new IP 10a, and we have taken current value of IP as 104. What is the reason behind this? Whenever we consider instruction cycle of an instruction, there are two main phases. First phase is called fetch phase, during which you pick all the bytes related to that instruction from memory, and after collecting all the bytes, execution phase starts, and your instruction is executed by a microprocessor. So when this instruction is fetched from memory, after fetching, completely fetching this instruction, IP will be having 104. So at the time of execution of jump instruction, IP will be having 104. So that is why we have taken IPC as 104. So we have calculated displacement IPN minus IPC, that means 10A minus 104 is calculated, and you are having 06 as displacement. And this displacement is within limit, that 06 is lesser than plus 7F hex. So that's why your instruction here will be stored as a short jump. So EB is the opcode for short jump instruction, and displacement value here is 06. So these are the 2 bytes for this jump instruction. Now we are having an example for near jump. Program is the same, but we have changed the current new IP value, that is now jump has to be performed to address 110A. In case of short jump, jump instruction was jump 010A, but in case of near jump, we have changed that destination address for jump, and now jump instruction is having 110A as new IP value. So we have calculated the displacement 110A minus 104. If you perform that calculation, you will be having 1006. So 1006 is exceeding the upper limit for positive displacement, that is 7F hex. So 1004 is greater than 7F hex. So that's why we decided that displacement is of 2 bytes. Displacement may not be stored in 1 byte. So your jump is of near type, but if your instruction is of near type, that will be stored in memory by using 3 bytes. So the calculation of displacement will be revised, and now IPN will be 110A and current value of IP will be 0105. As jump instruction is occupying 3 bytes and it is written at offset 102, so next instruction of addition, that is add dx comma cx, will be at offset 105. So now your displacement value is 110A minus 105, that is 1005. So that is the correct value for displacement. So we have shown that jump 110A instruction will be of 3 bytes. E9 is the opcode for near jump. Then the lower byte for displacement, that is 05. Then you are having higher byte of displacement, that is 10. So that is the difference between short jump and near jump. First of all, assembler will be calculating the displacement. If your displacement is within the specified limit, then that instruction will be stored as short jump. But if your displacement value is exceeding that specified limit, then your jump will be stored as near jump, and short jump will be of 2 bytes in memory, and near jump will occupy 3 bytes in memory. So last addressing mode is indirect program memory addressing. In this type of addressing, IP will be loaded from an operand, and that operand may be 16-bit microprocessor register or a memory address. In this type of addressing mode, jump instruction may be of near type as well as far type. So if you are having a near type instruction, jump instruction, then only IP will be changed, or otherwise if you are having a far type of jump, then IP and CS both registers will be having new values. So examples are given here. So operand may be a 16-bit register, jump AX is written. So new value for IP will be coming from the contents of AX. IP is of 16-bit, AX is also of 16-bit. So a new IP value will be loaded from AX register. Second example is jump near pointer within square bracket BX. Now we have mentioned that this jump is of near type, and the new value for IP will be loaded from a data segment. At offset BX, within data segment a word is present, and that word will be moving into IP. Third instruction is jump far pointer within square bracket DI plus 50H. So here the jump is of far type, as we have mentioned far pointer with memory address. So IP will be loaded from offset address DI plus 50 within data segment, and new value for code segment will be loaded from DI plus 52 offset address within data segment. So these are the jumps for indirect program memory addressing. Now we have to discuss stack memory addressing. In stack memory addressing, stack segment and stack pointer will be the focus of discussion, and the instructions we will be using to discuss stack operations, these are the push and pop instructions. So here in this slide you are having the operation of push and pop instructions. With push mnemonic, you will be writing an operand of 16-bit. So the higher byte of that operand will be stored at SP-1 offset within stack segment, and the lower byte of that operand will be stored at SP-2 offset within stack segment. And after 2 bytes of data transfer from the source to top of the stack segment. Stack pointer will be decremented by 2. Now for pop instruction, there will be an operand of 16 bit, and that operand will be the destination of data that will be received from the top of the stack. So during pop, first byte will be retrieved from stack pointer offset within stack segment, and that will be the lower byte of the destination. And higher byte will be retrieved from offset address sp plus 1 within stack segment, and that will be the higher byte of the destination mentioned in pop instruction. And after that, stack pointer register will be incremented by 2, so sp will be sp plus 2. So this operand within push and pop instructions may be a general purpose register of 16 bit, or memory address, or that may be a segment register or flag register. In case of 32-bit processors with push instruction, immediate data may be written as source, and that data will be stored on the top of the stack. And also there are push A and push pop A instructions are available for pushing all these registers in microprocessor on top of the stack in a sequence. And pop all instruction is used to retrieve all the registers present in microprocessor in a given sequence. So these push and pop instructions are available for 32-bit processors. These instructions are not available for 8088, 8086 microprocessors. Now for explaining the operation of push and pop instructions, we have taken an example. Here you may see that initial values for some registers are shown. Data segment register is having 3000 hex. Stack segment is having 8000 hex. Stack pointer is having 4000 hex. AX is having 30C0 hex. BX is at 200 hex, and DX is having 5060 hex, and base pointer is having 300 hex value. So these are the initial values for registers, and here we have shown data segment and stack segment. In stack segment, stack pointer is pointing to address 84000 hex. If you calculate physical address by using SS into 10H plus SP, so you will be getting 84000 hex. And if you calculate offset address of data segment by using BX register, so BX is having 200 and DS is having 3000, so physical address will be 30200 hex. So some portion of data segment is shown, and some portion of stack segment is shown here. And AX register is also shown in the diagram with initial value of 30C0 hex. So when push AX will be executed, lower byte of AX register, that is C0, will be stored at SP-2 location, and higher byte of AX register will be stored at SP-1 location. So as we have calculated in earlier that top of the stack is at 84000 hex. So when you calculate the physical address of SP-1, that will be 83FFF, and for physical address for SP minus 2 is 83FFEH. So AX is copied on top of the stack and SP decrements by 2. Now SP will be having 3 FFE look data contents in it. So the new location of SP is shown. So SP is pointing at address 83FFEH. Now we have to discuss second push operation, that is push square bracket bx. Here the operand is memory word, as we are going to access memory by using bx, so that word is residing within data segment. We have calculated physical address for bx register. So physical address is 30,200. At that address a word is stored and that word will be copied on top of the stack. So diagram shows that the lower byte of that word, which is residing at 30,200, that is F3, is moved to SP-2 location, that is 83FFC location. And higher byte of that word F5 is moved from data segment location 30,201 to top of the stack address 83FFD location. So that is data transfer, and after that word transfer from data segment to top of the stack pointer will be decremented by 2. So new top of the stack is 83FFC. Now we have to discuss pop operations. First pop instruction is pop dx. So a word will be transferred from top of the stack to register dx of processor. Before execution of this pop instruction, SP is pointing at location F3 FFC and the word stored there is 5A F3. So from SP location, that is 83 FFC, a byte will be moving into the lower byte of DX, and from location SP plus 1, that is 83 FFD, a byte will be moving into higher byte of DX. So as shown in figure, F3 is moved into DL and F5 is moved into DH register, and DX is retrieved from top of the stack. After completion of popping data from top of the stack pointer will be incremented by 2. So now new stack top is at 83FFE. Now second pop instruction is pop square bracket BP. Here a byte of data will be moved from top of the stack to a location within a stack segment at offset BP. Whenever we use BP register to point memory address, then that address will be within a stack segment. So as before execution of this instruction, SP is pointing at F3 FFE. So as from SP location, a byte will be moved at BP address within stack segment, and from SP plus 1 location, that is F3 FFF, a byte will be moved into stack segment at offset BP plus 1. So as shown in figure, C0 is moved from location 83 FFE to location 80300 within a stack segment, and a byte 30 is moved from top of the stack location 83FFF to a location within stack segment 80301. So a word is popped from stack into stack at offset BP. After completion of this pop operation, SP will be incremented by 2. So new stack top is at address 84000 location. So we have covered all the addressing modes, data addressing modes, program memory addressing mode, and stack memory addressing mode. Now we have to start new topic of assembly to machine language conversion. So whenever you write a program, then that program is converted into machine code by using assembler. So first of all, we have to discuss the syntax of assembly language instruction. In assembly language instructions, there will be four fields. First one is the name field. Second one is operation field, that is the mnemonic of instruction. Then there may be one operand or more than one operands present in any instruction, or some instructions are having no operand. So third field is operand field, that may be present or not. After semicolon, whatever you write, that will be treated as the comment. So that may be an explanation of the instruction or something else. In machine code of the assembly language instruction, there will be hexadecimal numbers. So first byte will be of opcode, then second byte will be having mod, reg, r/m. These are the codes explaining the operation of instruction. The second byte is optional byte. Somewhere in instructions this will be present. In some other instructions that may not be present. So for mod field there are 2 bits. For reg field and r/m field there are 3 bits of code. So total 8 bit code is present in second byte. So after that, if your instruction is having displacement, that will be written. Then after that, if your instruction is having some immediate data, that will be stored. Displacement may not be present in instruction. If displacement is present in your instruction, that may be of maximum 2 bytes. In some instructions, data may not be present. If data is present in your instruction, then that immediate data may be maximum of 2 bytes. Now in this slide, we are having code table for mod. As we have discussed earlier, that mod is of 2 bits. So there are 4 options available: 00, 01, 10, 11. If you are having no memory access in your instruction, then r/m field will be having code of register. So mod field will be placed as 11. So that will be a declaration that no memory access is present in the operation of the instruction, but r/m field is having the code of a register. But if there is some memory access during the operation of your instruction, then mod field may be 00, 01, 10, depending upon the addressing mode and the presence or absence of displacement in your instruction. After that table, here in this slide you are having W bit and D bit. W bit shows how many bits are transferred from one location to any other location, or how many bits are manipulated during the operation of this instruction. So W is 0 for byte and W is 1 for word. Then there is D bit. D bit is for showing the flow of data direction. So if your data is flowing from reg field to r slash m field, then d will be 0. Or otherwise, if data is flowing from r slash m field to reg field, d will be 1. So here